Welcome to Breadboarding. In this video I'm going to be summarising the most recent Breadboard PC project, but I was just going to start with the version 1 project which I broke apart and disassembled recently. I thought I'd just share a few photos of that. So this was the Breadboard PC which completed around January 2025. And we have an Intel 8088 CPU, and this region here has got the clock and buffers. Then we've got the ROM and the RAM, so the EPROM has the BIOS in it that handles the startup of the PC and loads the operating system. Then we had some serial ports and a peripheral interface adapter to handle the 7-segment LED display and keypad, and that was used to provide a basic simple monitor to allow us to do a certain amount of debugging before we got the full BIOS and MS-DOS running. Then we added some PC-specific things, so direct memory access, timers, power on self-test ports, the programmable interrupt controller and speaker, so you could get beep codes. And then also added a PS2 compatible keyboard and mouse controller. Then we also developed a monochrome display adapter video controller. This is a fairly simple video card in that it only does text, it doesn't do any graphics. Then we also had to make sure we did good quality power distribution to make sure that there's sufficient power going to each of the breadboards here. Then we added an IDE Hard disk controller, a floppy disk controller, and we also then developed a CGA video controller, and this is capable of doing both graphics and text, and also produces VGA compatible output. So although it's software compatible with CGA, the output signals are compatible with modern LCD monitors and video capture devices. So I pulled this apart, and this is basically what it looks like when it's pulled apart. Basically, you've got our Intel 8088 CPU here on a single breadboard there. There's about 80 other chips in total with the MDA adapter here as well. I had about 24 breadboards and 18 power strips in total. Lots and lots of these wires and these DuPont rainbow cables which we use for wiring up a lot of the bus signals. And I've kept the monochrome display adapter video controller whole for the moment because it might be useful in debugging some of the later projects. So this is the video 27 in the Breadboard PC 8088 version 2, and this is basically going to be summarising the 26 videos that I've released over the last sort of 11 months or so, and hopefully will take about 30 minutes from now on. So the Breadboarding Labs channel, I started this around August 2022, trying to build reliable digital electronics projects, primarily retro electronics projects at the moment, so things from probably at least 30 to 40 years ago, using good quality breadboards. This is particularly important if you use cheap and cheerful ones and you're likely to have problems trying to build such complex circuits. The version 1 of the Breadboard PC I just shown you, this ran from around December 2022, completing in January 2025. I then started the version 2 project, which had a number of improvements in it, around February 2025 and just ending now. So this is really just going to be covering the building of the version 2, which had a number of improvements over the earlier version. The IBM PC was released originally in October 1981, and this had twin floppy disks. It didn't have a hard disk. It used the Intel 8088 processor, which is software compatible with the 8086, but it talks to the outside world using an 8-bit data bus rather than a 16-bit database such as the 8086. And this makes it easier and cheaper to actually build a computer. There are a couple of breadboard projects out there, although none of them are actually able to load MS-DOS from what I can tell. Sergey Kiselev has produced a very useful project, the XI-8088. And this is a printed circuit board design, and it's very useful for working out how to use some of the components we need here, particularly some of the newer ones like PS2 keyboard and mouse controllers. So this is the original prototype, the wire wrap prototype board from, there's a site I think which will be in the description below. And this showed the original wire wrap design where you can see the ISA bus connectors, the processors here, and the various ROM chips which are for the BIOS. And then this is the reverse side, so you can see here that the wire wrap was really quite messy. So although some of the wiring on the Breadboard PC will look quite messy at times, I don't think it's quite as difficult to follow as the original wire wrap board here. Now this is the type of breadboard that I use, so they're busboard prototype systems. The BB830 is the model that I tend to use a lot of, and you can see here this is the Intel 8088 processor that I used in the version 1 project. You can see P8088 and 1983, I think this particular part was made. Now this particular Breadboard PC design is kind of like a hybrid design. So we've got bits from the original IBM PC from 1981, largely the same as the 1983 PC XT. The main difference of the PC XT is it had a hard disk. And from that era, we're using the same processor, the 8088. The clock and bus controls are very similar. The monochrome display adapter, color graphics adapter, 8-bit ISA bus, the timers, the parallel port B and the speaker all come from that era. Then when the PC AT came out, so this was a 286 based PC around 1984, there's some enhancements that we were making use of. So we're using a real-time clock, so we don't have to set the date and time every time we boot MS-DOS. Has a slightly faster serial port, has dual interrupt controllers so that there's enough interrupts to be able to handle things like mouse and other peripherals. And it also has a power on self-test port. So this allows us to see how far the BIOS has got during boot up. So if it halts at any stage, we can at least get an idea of how far it's got. Then in 1986, the Compact Despro 386 was the first 386 based PC, but it introduced the IDE Hard Disk and IDE Hard Disk controller, so we're making use of that. And then finally in 1987, when the IBM PS2 range first came out, then that introduced the PS2 keyboard and PS2 mouse connectors. It also introduced the VGA video standard, so that is the output signals that we're producing from this computer, so we can make use of it in relatively modern video capture hardware. And it also introduced around that time the 3.5-inch high-density floppy disk drive, so this is 1.44 megabyte floppy disk as it's normally known, or strictly speaking it's 1440 kilobytes, I think, technically speaking. And that's the floppy disk drive and controller that we'll be using. So let's have a quick look at the chips that we're going to be using, and as we go through the video I've taken out most of the schematic diagrams and most of the explanations. A lot of the build sequences will be sped up 60 times, so for every second that we see in the video, then quite often that's a minute. So this is sped up quite quickly. If you really want to go through and see these things in detail, there'll be a playlist in the description below, and you can go off and watch all the videos from start to finish if you want to. So good luck, and we're now going to go through the speeded up sequences. So these are chips we're going to be using, the modern ones on the right and the older legacy ones on the left, and you can see the surface mount chip there. So this is the breadboard we're going to be using for the CPU and the buffers and latches, and you'll see there's the two clock crystals that we got there for the basic speed and the turbo mode. You can see we've got our bus on the left hand side there made of strip board with soldered pins in there. So now just wiring in the reset circuit there and the power on reset. So that is a supervisor circuit there that will reset the CPU if the voltage is not high enough. You'll see here we tend to use white for the data bus, green for the address bus, and blue is used for various control signals. Now what we're going to do to test this, the no operation code for the 8088, 8086 will just actually cycle through all the address lines. So when we attach the logic analyzer there, we can see all the address lines are just going up in sequence there. And that just means we've tested the clock and we've checked that the CPU is working. So now we're going to wire in two 512K RAM chips here. So that will give us a total possible of about 1 megabyte of RAM, although we can't use all of it. We've also got the EPROM, or the read-only memory, on the left-hand side there. That's in a 0 insertion 4 socket, so it's easy to take out and program. Then we're just adding the address decoder at the top there, just finishing off that. Now we need to plug in our 7-segment display and keyboard. Now this came from the original Nanocomp project, which was a 6809 project, which will be links in the description below. But this basically allows us to do a very simple display and keypad and actually inspect memory and do various other operations to debug the system before we actually manage to get the BIOS and MS-DOS. This is the Adafruit keypad that we're using, which is quite a nice keypad. Now we just put some red auto repair tape on there that actually acts as a filter. Just going to test that the keypad's working. You can see we're trying all the different key codes there. So all the key codes are working, so that's good. We check that off. So now we're in a position to start to look at the monitor. So the Nanocomp Monitor was based on the 6809 version. And now I've updated it to run on the 8088, and there's various links there you can have a look at. You can see here we can inspect memory, run programs, load and save programs to a serial port when we've done it. And we also then have the extra segment and code segment we can set. So these are some of the changes that we did compared to the earlier version. And because it's included in the main BIOS, just for simplicity, we're going to program the BIOS with the monitor built into it. We could originally have just done the monitor, but it was easier to include it in the BIOS for this stage. So when we plug this in now and power it on, we can see we've got Nanocomp 8088 version 6. We'll just inspect some memory so we can read the memory. Then we can look at the register values. Then we're going to set the code segment and extra segment and look at some memory there where I've already loaded 0, 1, 2, and 3, and 4. Then we'll go in and change it and then make sure we can actually go back and see it. So we can see we've changed the values there. Then we'll look at some of the EPROM here, and if we try and change a value in the EPROM, then it will just sort of show us it hasn't worked by returning us to the dash there. So now we need to plug in the reset and non-maskable interrupt buttons. Originally the keypad had 2 keys for that. However, because of this matrix keypad, you can't easily wire these in. So we've just done the separate reset and non-maskable interrupt lines, which takes us back to the monitor. So now we've got the Nanocomp monitor working with the keypad. We're now going to add a serial port. So we're using a fairly modern surface mount chip that we've already put onto a DIP adapter. The DIP is dual inline package. So we're just going to wire in the breadboard there, put in a breadboard buddy for the power. Now this is a USB to serial adapter here on the left hand side there. So that allows us to connect that up to the PC and access the serial port quite easily from a modern PC. So just wiring in all the various control signals. So the I/O tends to be in yellow, and wiring in the various other lines there, checking everything is all connected properly. So we're just going to check the frequencies first. So this is the clock frequency, and then this is the divided frequency, which is used for 9600 baud. Now we're just going to save a bit of data from the BIOS and just look at it in the S-record format. You'll see the S-record format actually has some syntax highlighting in Notepad++. There's a checksum on the end there that will tell you if you've got an error. And if you have the wrong number of bytes on the left here, it'll also tell you you've got an error. So it's quite a useful format for downloading programs in. And then this is one of our monitor LED test programs. So I've actually assembled this in S-record format, so we can download that just to test the serial port. So you'll just load that into the extra segment 7000, run it, and we can now see the same software that was running from EPROM is now running from RAM as well. So now we're going to add the bits of the PC that are needed to make it PC compatible. So we're adding a timer, a port B, which has a number of configuration options on it and is also used to help drive the speaker. We're also then going to be wiring in the speaker circuit, and the power on self-test port is down on the bottom right hand side there. You can see the speaker and the transistor driving that up on the top right there. So this is a test program that's going to do beep test, so we should hear a 400 Hz tone when we run this. We're also outputting a descending sequence of numbers to a power on self-test port. So we're just going to run that up. You can hear the 400 Hz tone there. And if we look in the logic analyzer, you can see now this is on the power on self-test port, and we can see that we're getting the descending sequence of values on there. So when we get power on self-test messages from the BIOS, we'll then be able to pick them up. So now we're going to need to wire in some of these additional bits. So this is the real-time clock, and there'll be a backup battery, a data bus buffer, and the interrupt controllers. We need 2 interrupt controllers, so we have sufficient interrupts to be able to handle things like the mouse and the keyboard and serial adapters. So just wiring in the real-time clock there and the data bus buffers. In the version 1 PC, I didn't include enough data bus buffers, and I did have some stability problems. So now we're wiring in the interrupt controllers, and the red lines tend to be interrupt related if they're not power. So when we wire all this up, we're then going to plug some of these into the bus rails down the bottom there in this strip board. So we're just going through checking that everything's there. We've got our RAM and ROM down the bottom and our display there. Now we're just going to plug in the logic analyzer, and we're going to actually start setting up the external I/O board. We're going to move the serial port actually up onto that board. Now just going to take the external I/O board off there, and what we're going to be doing here is wiring up the IDE connector there, the PS2 keyboard and mouse port. There's a floppy disk controller at the top there. And we're going to start actually with the PS2 keyboard and mouse controller. You'll see there's some buffering at the bottom there. One important thing about that is that they're an open collector, and therefore you need to include a pull-up resistor if you're trying to use an oscilloscope on any of those signals. Just going through and wiring up all of the power pins first of all, then wiring up the PS2 keyboard and mouse connector, then wiring in the clock for the crystal for the keyboard controller. Requires an 8 MHz clock there. Putting in the rest of the passive components needed for the keyboard. And you'll see that sometimes when we're fitting in the fitted cables, we need to unplug a few things to make the cables fit neater. Now we're going to wire up the serial controller. They're just going to put in that USB to serial converter in there as well. Again, the yellow lines I tend to use for input-output. Then we're going to wire in the interrupt there is the red one, the green ones are the address lines, and then we'll be wiring in ribbon cables probably for the data bus. Just going to go in and put all of the decoupling capacitors. That's necessary to minimize interference on the power lines. Now just wiring in the address bus, the data bus, and then we're now going to put it back in and plug it all back into the main Breadboard PC. And now that we've got this sort of strip board bus rails, it makes the connections a lot more reliable than when we were using just multiple power strips together as the bus. So just check that it's working. And then we're going to go through and update the BIOS. What I did here is update the BIOS to an output to the serial port. So even though we haven't got a video card at the moment, we can still see if the BIOS is actually sending output to the serial port. So we're just going to program the BIOS with that serial port enable, and then when we start it up, we should now be able to see the BIOS messages. You can see there in the terminal emulator there that we haven't got the checksum set up properly in the BIOS yet, but we can see the various messages coming up there. And if we type help here, we can also see what the various help options are for the BIOS configuration. So now we're going to look at the video card. So CGA video card was in the first PCs, and it had a Motro 6845 CRTC, 16K of RAM, and hard-coded characters. Although this came out in 1981, the colour display was only available in 1983. And because its output is not really compatible with modern display devices, I've actually changed the design to output VGA compatible. So that's what we're going to be doing in this particular project. Now this is an enhanced version of the version 1 in that I'm now using a 100-pin programmable logic device. So this goes on this surface mount breadboard adapter. And in fact, this other chip down here, we managed to merge into this 100-pin chip here. So I'm just going to put in the power rails and the chips and put all the labels on. Now to start with, what we're going to need to do is to just do a number of the chips to get some video output. So we'll use the 15-pin VGA connector, the data bus buffers, the CRTC, and the video digital analog converter. So we're going to use the PLD to produce a few clock signals, and then we should be able to get some video output to test that things are working. If we do everything one big bang, it's very difficult to debug. Now the little chip down below the video DAC there is a constant current source needed for the video output. So wired in the PLD there, there's quite a lot of power lines needed. Down the bottom right hand side, you've got the JDEC programming port for the PLD. So this allows us to program the PLD in circuit. I have installed a 25 MHz clock there locally just for testing. So I went off and did a number of tests to make sure the clock signals and things were correct coming out of here before we actually wired it up to any sort of a monitor or video capture. This is where some of the test cables and things are in here. Now we're going to wire things up because we've got a good video sync, vertical sync and horizontal sync, and all the various other clock signals are working okay. We're now just going to wire in the horizontal sync, vertical sync, and we've wired in the character clock and some of the other signals going into the video digital analog converter. So now we're in a position to just test that everything's working before we plug it in. So it is, you can see down the bottom right hand side of the display. And then we're going to wire up the CGA card into the rest of the bus. And then we're going to do some simple tests to start off with, just to make sure we've got some video output. Just tweak the constant current source, check a few other connections. So now we're just going to test that we got some video output, so that's all white there at the moment. We can then change the colours onto some of the address lines, so that gives us the different alternating colours. So we know we're getting the colours coming out of the video DAC, but now what we need to do is to start to wire up the character generator. So the chip on the bottom left there is the EPROM with the bitmap for the characters. So what we're just doing then is wiring that into a shift register just there with the red connections there between the shift register and the character generator, wiring in the various address lines and things between the CRTC. And what we're now going to do is to download a test program that should hopefully now show us that we've got our repeating characters just repeating from 0 to 255. If we change this now from blue to white, we can now get this coming out in white. So this is what's left. Now we run the program and it changes to white. Now if we actually want to, we can now plug the video attributes into a little test board, and we'll actually be able to vary the colours that we're actually getting out of there. Now, so what we're now doing is wiring in the video attributes, so it's actually coming into the PLD there. What that then means is we can, with a little test board, we can actually try different colour combinations. So you'll see there, that's the default of white, but now we can now change it to white on blue, various other combinations of grey, white, black backgrounds. Blue on blue, it's not very useful. And then we've got various combinations of the green, red, lilac, green and light green, red and light red, blue and cyan, I guess that colour is, and then an orangey colour, purpley colour. Back to here, then we'll try out the background. So there's different backgrounds. The green. And one of the things with the background, when we get the lighter colours in the background, if the blinking is enabled, then we would end up with a blinking character. If blinking is disabled, then we end up with a lighter colour. And I think there's one colour, you can see that yellow is not a great background colour. So it looks like the various colours and the attributes are actually being represented. If we plug the attributes into address lines, we can show that the colours are varying with the CRTC addresses. So we now need to plug in some video RAM and actually get the video RAM wired up to the card here, so that then we can program test patterns and things. That's the little test board that I was using for setting the attributes with 1s and 0s. Now just putting in the address bus lines for the top of address bus, so A8 to A15 and A0 to A7. Make sure we're putting in the control signals for those latches properly. Wire those into the PLD. Then the CRTC address buffers are again controlled by the PLD there. Those are the control bus signals coming from the main bus. Wiring those control signals to the PLD. Now we're going to need to hook up the address lines to the video RAM, and then the higher address lines have got the pins arranged in a bit of a random order. So I've made a cable there that fits the upper address lines on the video RAM there. And we need to connect up some of the data bus for the video data there. Then the row address lines for the character generator. Now we're going to connect it back in. We're just going to check that it's still working okay. Yep, so it's working okay before we connect it. Now we're going to wire up the data lines, the address lines, and the control lines. Just need to make sure that we're getting the control bus signals the right way around. This is the test pattern that we expect from the version 1 series, so you can see it's got all the different characters and different attributes. So we're just going to load that first of all and run that up. So it's going to clear the screen first, then we get test pattern, then we're blinking video, then grayscale, then it should be 40 column mode, and that looks pretty good. There are a few minor issues to do with attributes bleeding. So then we run it full screen, the blinking mode, grayscale, and then 40 column mode as well. So that's back to normal. So there's a few things we need to correct in future videos, but it's looking reasonable there. Now we're going to power it on and boot the BIOS. You'll see there that the checksum for the CMOS RAM in the CRTC is not right, and also the real-time clock doesn't have the correct date in there. So what we're just going to do first of all is to turn off drive 0, so it thinks it's got a 1.44 megabyte floppy disk drive. So we'll just go into the help utility and to turn off the floppy disk drive to start with. Then we're going to go in and set the date and set the time. And then we're going to write that to the CMOS and then reboot and check to see that, yes, we've now got the right real-time clock time. And obviously drive 0 is now set up as none. So now we're going to plug in the floppy disk controller. So we've taken the I/O board out, and now we're just going to wire up the floppy disk controller. This one chip actually does virtually everything we need it to do, apart from the disk change detection, for which we've added something to that PLD below the connector we're wiring up there. You're just wiring in the clock needed for the floppy disk controller, all the control signals. There's a lot of wiring out of the floppy disk connector to the outputs of the floppy disk controller, then wiring in the data bus there. So that's the floppy disk controller cable going to the floppy disk drive with MS-DOS 330 in it. It is a crossed cable, so this turns drive B into drive A. Most modern drives are configured as drive B. And we're just going to check that this is the CPU speed on the standard speed, which is 4.77 megahertz. Then we're going to enable turbo mode, which enables the higher frequency clock. And you see the turbo on the top line there for ATC88 turbo. And if we just check the oscilloscope, we should see that the frequency we'd expect to be about 8.3 megahertz. So yes, we can see the clock is 8.3 megahertz. We need the CPU to running slightly faster to do programmed I/O, and now we've booted up into MS-DOS 330. There's not much on this, is very empty disk, so I'll put in a different floppy disk in a few minutes and we'll actually do something a little bit more interesting. Now we're going to try booting MS-DOS 5. So there's quite a bit more disk accessing here. I've speeded up quite a bit. So now we've been able to boot MS-DOS 5 as well. That looks like we've managed to get the floppy disk controller working with both versions of MS-DOS. So this is our external I/O card, and now what we're going to do is to wire up the IDE hard disk controller. So the IDE port is connected to two data bus buffers. So the IDE port has 16 data bits. You can see there the connector I've made there, and we need to divide that into the lower 8 bits and the upper 8 bits. So just going to wire in all of the upper data bits there in white. Quite a few of the pins are tied to ground. Those are the lower data bits wired into the other buffer there. Then we'll wire back in all those control signals. Some of the green chip enable and address lines, and then putting in the data lines there as well. So we do need to actually install XT-IDE Universal BIOS. So this knows how to talk to the IDE hard disks. We're just going to make the XIDE BIOS and the configuration utility. We need to use a configuration utility in DOSBox to configure the BIOS settings so that it knows which port to use and which mode to run in. You'll see we load the BIOS from the file. It's only 3995 bytes at the moment. We do all the configuration here, setting the port, and we'll also be setting it to XT-IDE Rev 1, which is the slower mode. And then we're going to set it to black and white and then save that configuration. And if we then just try and load the configuration again, you can see it's now 496 bytes. Now that needs to go in the first 4K of the EPROM for the BIOS. So you see that at the moment it's all FF. So now we're going to load it from the XT-IDE BIOS. And then at 4K we will load the main BIOS as well. So that's loading in the XT-IDE BIOS, and now we need to load in the rest of the BIOS at the 4K boundary there. So now we program that. We should now be able to see hard disks. Now these are the instructions we're going to be going through in a minute. So one is to clear an existing Windows hard disk. So later versions of Windows, MS-DOS can't actually see later versions of Windows disks. So we need to actually clear a disk first. So we're selecting disk 1, and then we're going to clean that disk. Make sure you don't clean disk 0 or you'll wipe your operating system. So we can see that that disk is now clear, and that should now mean that MS-DOS is able to use the fdisk utility to create a partition and to format it. First of all, just going to plug in an existing drive that I already had configured from the version 1. So that is now booting up. So that's good. You can see that it's detected the drive at the top there. 300 hexadecimal ST9500. You can see we've got all of the files already loaded on there. Now I'm just going to go into the tools and we're going to run a disk test media scan. This just makes sure that the disk controller is actually working properly, and this is sped up 60 times, so this would have taken about 8 minutes to run. And if you get an error, then you would have an exclamation mark there. So there's no errors there, so it looks like the disk controller is working okay. So now we've connected up the blank disk that we've just wiped, and we're booting off the floppy disk. So we're just going to partition the disk first using fdisk. Create a primary partition. Then we need to restart. Once we restart, we now do format/s, so that will copy the MS-DOS system file. So we now should have a bootable disk. Do check disks. That shows we've got a 32 megabyte disk. Now, what we're going to do now is just copy the A drive files onto the C drive. So the xcopy/s will do that, and then we're going to use Norton Editor to change the config.sys and the autoexec.bat so that we can change the A drive to the C drive. Change that there, save it, now open the autoexec.bat and change the A's to C there as well. That should now mean we should now be able to boot off the C drive, so you can see we can there. I'm just going to run some of the CGA test utilities. That's the color mode and the various color palettes, and the direct write doesn't use the BIOS for writing to the video. It tends to be a bit cleaner. Then we'll do CT6, which is the high-res 2-color mode. There are a few little pixels there not coming out quite right. We'll look at that in later videos. So now we're going to run the CGA compatibility program, and the main one here really is the CGA snow. We did quite a lot of effort to actually eliminate the CGA snow that occurs when the CPU is accessing the video RAM at the same time as the CGA CRTC controller, so that's clean. And then we've got the various color graphics modes, the high-res graphics modes in the different colors. The right line there sometimes doesn't get shown because of the video sync with the video capture device. And this shows the different color palettes that we've got for the color mode. Then this indicates the vertical retrace. Now, although it's a CGA adapter, it's actually refreshing at 70 Hz, which is a VGA compatible frequency. And if we see these color bars here, then it means that the CGA adapter is a proper Motorola 6845 CRTC, which it is. It's showing that we're highly compatible with the CGA standard here. Then the row reprogramming shows a high color sort of text stroke graphics mode, which allows 16 colors. And then this test actually changes the start address of the memory in the CRTC and allows you to actually scroll the data more quickly than you might be able to do using byte manipulation. Then there's a few other tests to do the various color modes, different line combinations for focus, color moire. The linearity just sort of checks that everything's sort of coming out nice. There's a few bytes here which don't come out quite right in that multiburst, and there's a few bytes in that pattern that aren't quite right, which we'll see when we come to run Windows 3. Now this one, earlier in the series, then this test would leave a lot of pixels behind. When there's any problems with reading the video RAM, then you end up with a lot of pixels left behind. So the fact that this test is running cleanly like that, then it means that the video RAM access is working quite well. And then there's just a camera calibration plate, and we won't do the benchmarks there. So now we're just going to run one of the VGA test utilities that we used early in the series. There's just some CGA tests there, and we're just going to run through those, and most of those CGA tests come out reasonably well. The menu's a little bit difficult to read there. And again, we got the odd little pixel not quite coming out right there. Okay, so that looks like it's all okay. So we'll just now run the disk test again, and now what we're going to do is to run the Windows 3 setup. So I have installed Windows 3 a little bit earlier, but we'll just look at the setup program. So it's a lot more like the modern Windows setup. You can see you've got MS-DOS, CGA, PS2 mouse, and enhanced UK keyboard. That's what we're running with. So if you now type Win for Windows, you can see Windows 3.0 starting up. It's only black and white because we're using CGA video. You can see there's a few pixels not quite coming out right. Now if we just look in Help About, we can see that Program Manager says we're running in real mode because we're using an 8088 and we have 383K of free memory. Having completed the Breadboard PC version 2 project, and now look at what we're going to be looking at next year. So what we're going to look at next. So what I've been researching is the Compact Desk Pro 386. So the Compact Desk Pro 386 is the first 386 computer using the Intel 8386 or i386 as it's commonly known. And this was the first computer to actually be using a PC with 32-bit RAM. It was announced on the 9th of September 1986, so it's going to be coming up for 40 years old this year. And the Compact Desk Pro 386 has probably done more to define the PC standards over the last 40 years than even the original IBM PC, that this really was the standard that has actually prevailed going forwards. The IBM PS2 standard really died out around 1994. IBM stopped making PS2s around 1994, so this computer is actually the grandfather of most modern computers. And in fact, most modern PCs are still able to actually emulate all of the chips and things that we've been talking about during these videos. Just so happens that there's a lot of detailed technical schematics and even some PLD descriptions for the early versions of the Despro 386. So I will be looking at trying to build a Breadboard PC 386 version starting in January 2026. I will be trying to load Windows 3.1 and Windows 95 even if I can install enough memory, and these do require a minimum of 386 to run. And the only complication really here is we've got our Intel i386 here. I have a DX33, so that's capable of running up to 33 megahertz, although that does require a 66 megahertz clock. So I'm probably going to be running this chip at a fraction of this speed, probably using something like a 16 megahertz clock and 8 megahertz sort of clock speed. And the other complication we've got here is the i386 is actually in a 132-pin PGA format. So that means that there are 132 pins in 3 rows around the chip here. So we are going to need to make quite a complicated adapter to plug into breadboards, but that's what I'm planning to do. So if you don't want to miss out on future videos, please hit subscribe and then you won't miss out on the new series as they're published. If you could click like as well, it just helps to make the videos available to more people. Thanks for watching.